the statement of the problem. It will always be in the statement of the problem somewhere. So this one is 0.1 molar. We don't care about water. The problem didn't tell us anything about hydrogen ions being in the solution or aspirin ions being in the solution. The change that occurs comes from the balanced equation. You're going to use up some of this, make some of each of these, and you make an equal amount to the amount you use up. And so at equilibrium, we just add the two rows together. Oops. We can write, once we have the balanced equation, the equilibrium constant expression, and then we can substitute in what we know. And this part here comes from the last row of the equilibrium table, the ice table. Whatever you put into the Ka expression has to have come from the ice table. So now we can solve this. So what, 3.0 times 10 to the minus 4 is approximately equal to x squared over 0.1. This assumes x is much, much less than 0.1. As long as the assumption's okay, we're in good shape. So x squared equals, and x is 5.5 times 10 to the minus third. Actually, the question was, what is the pH? So we want the negative log of the hydrogen ion concentration. And if I work my way back up here, the hydrogen ion concentration was x. What did I do wrong? I knew it was 0.3. I got the 3 in the wrong place. 2.26. A couple things before I forget. Without a calculator, what's the negative log of 5.5 times 10 to the minus 4? Somebody said it. Jessica said it. Anybody else know it? You don't need a calculator to do this. The answer is staring you in the face. How much? Not 2.26, because 2.26 is the negative log of 5.5 times 10 to the minus 3. So the negative log of 5.5 times 10 to the minus 4 is 3.26. Okay? The power of 10 tells you what the first digit is in the pH. That first digit in the pH is not a significant digit. Because if I were to ask you, what is the pH? What is the negative log of 5.5 times 10 to the minus 11? Hopefully, at this point, without a calculator, you can tell me 10.26. The power of 10 determines what the digits in front of the decimal are. They're not at all significant. The only thing that's significant, since I started with 2 digits here, I should end up with 2 digits there. The other one just places the decimal point for you. Okay? And so once you've learned, for example, I asked you, what's the log of 5 times 10 to the minus 1? Check me on that one for me. Hopefully I'm right. Yes? What'd you get? Yep, that's right. Thank you. The log of 5 is going to be around 3, or 0.3. So the negative sign here is because I did such a high power of 10. You asked me to remind you again. Okay. How I figured out the decimals as opposed to the power. I don't understand your question, actually. Okay, I get what you're getting at. If we look back at this one right here, the log of 5.5 times 10 to the minus 4. 5.5 times 10 to the minus 4 is somewhere between that range, right? You can all tell me, I hope, that the negative log of 1 times 10 to the minus 4 is 4. The negative log of 1 times 10 to the minus 3 is 3. So the answer to the negative log of this has to be somewhere between those two numbers. We've already done the buttons on our calculator to say that it's 3.26. Your answer, and we had talked about doing this without a calculator for a multiple choice type exam. Your answer, if you can bracket that concentration to powers of 10 that you can do negative logs of in your head, you can automatically say the answer has to be somewhere between 3 and 4. And if you remember that 5, when you take the negative log of it, you get 0.3 in the decimal. You can say, okay, if the concentration was 7 times 10 to the minus 4, you would end up with a pH that is closer that way. If you started with a concentration of 2 times 10 to the minus 4, you'd be a pH closer to 4. So that you can bracket these things to try and get estimates of them. In terms of significant digits, just a second, the only thing that's significant is you have 2 digits that are significant here, so I have to end up with 2 digits that are significant. This one is related to the power of 10, so it's not a significant digit. You don't have to count it. Do you get, yes, I will never not let you use a calculator, but those of you planning to take the MCAT, you don't. The MCAT, you have to do the test without a calculator. So I'm trying to show you how you'll be able to do that. Uh-huh. All right, back to the important thing here. If we assume that x is much less than 0.1, then 0.1 minus x is approximately 0.1. I'm just assuming that that x is such a small number, it's not going to, when you subtract it from 0.1, you don't have to worry about it. So we just drop it out. It makes the calculation easier. Those of you who have quadratic equations in your calculator, if you want to do that, that's fine. Feel free to use the quadratic equation in your calculator. How do you know when you can assume that? The rule of thumb, or the book will tell you, is that any time the percent dissociation is 5% or less, you can make that assumption. I'll tell you, always make it. Why? You're going to like this. You'll remember this probably from your calculus class. Something called the method of successive approximations. What the method of a successive approximation says is that you can make that assumption anytime you want. If you then take the answer you get, in our case, this number, and substitute it back in to that equation in the denominator and solve for x again, you'll get a better answer. So if we try that, so step 2 would be 3.0 times 10 to the minus 4 is equal to x times x times 0.1 minus 5.5 times 10 to the negative, what was it? 3. So 3.0 times 10 to the minus 4 equals x squared over 0.9945, right? Nope, 0.945. Can you do that one for me, Amelia? So x equals the square root . Now when you solve for x on the second iteration, you get an answer of 5.3 times 10 to the negative 3. Notice that when we did it the first time, assuming that x was small, we got 5.5. When we did it the second time, we get a slightly different value for x. Well, guess what you need to do? Do it again. X squared, or excuse me, 3.0 times 10 to the minus 4 equals the square root. Whoops. And now when you do this one this time, you get x equals 5.3 times 10 to the minus 3. We had 2 iterations of this process where you got the same value out of it. And so this is the value of x. If you solve a quadratic equation, that's the value you'll get for x. Now, before you all sit out there and say, do I have to do this on a test? No, you don't have to do it on a test. When do you know that the assumption is valid? Whenever the percent association is 5% or less. What's percent association? Is equal to x over 0.1 in this case. Where did the 0.1 come from? That was my initial concentration. X is the amount I got when it dissociated. And so if I take the percent association as how much did I make, divided by how much did I start with, so I get 5.5 times 10 to the minus 3 divided by 0.1 equals 5.5%. Is it close enough? Yeah, it's close enough. Should you do it a little bit more accurately? Probably. How do you know with a value of k? Whenever k is 10 to the minus 4, and you've got a 1/10 of a molar concentration, you're going to be close to that 5% range. There's a relationship between, well, let's go ahead and get to this equation. Let me show you this equation. I was going to avoid it, but since it's come up, we'll bring it out. Here's any generic weak acid. Doesn't matter what acid it is. There's a monoprotic acid, so a single acidic hydrogen. There is an anion attached to it, a weak acid anion or a weak base anion. Put it in water, you get hydronium ions and acid and the anion. You can write the acid dissociation constant for this reaction. It looks like that. Now, I'm going to do a little math magic on it. I'm going to take the negative log of both sides. Whenever you see a negative log, we're going to abbreviate that to be pKa. The lowercase p means take the negative log of both sides of the equation. Now you've got to remember some algebra. The log of a times b is equal to, or, oops. Okay. So all I'm going to do is I'm going to factor this out. Why did I bother to do that? What's the negative log of the hydrogen ion concentration? pH minus the log sorry, there should be a plus sign in there. I knew I was supposed to have it in there and I just took it out for some reason. Log of A times B is equal to the log of A plus the log of B. Sorry, I knew that was supposed to be in there and I'm correcting myself as I'm going. I'm going to factor out, I'm going to break this up so that this is now the constant B and this is the constant A. So what I wrote here I need to fix. Let me fix this so that it's right. The log of A times B is equal to the log of A plus the log of B. And so I can factor out, so if I have 2 times 3 over 5, I always go back to simple numbers. 2 times 3 over 5 is equal to 2 times 3 over 5. It'll give me the same thing. So this equation, first of all, I'll tell you it is not your friend. It is a simple equation. It's a beautiful equation. You will want to use it all the time, especially if you are a life science person. Because we give it this fancy name, and all of a sudden, as soon as I give it a name, everybody says, oh, if it has a special name, it must be important. And it is. It's the Henderson-Hasselbalch equation. It works great for weak acid equilibria. It works phenomenally for buffers, unless you forget where it comes from. What does it tell you? It tells you that, if I rearrange this thing, if you look at that for a second, it tells you that the pH of any weak acid, weak base, or weak acid and conjugate base combination is going to be related to its acid dissociation constant. So back here to all of these, if I take any one of these numbers here and I convert it into a pKa, Amelia? What's the pKa of acetylsalicylic acid? 3 times 10 to the minus 4. Okay. So the pKa of acetylsalicylic acid, if I just take the negative log of 3 times 10 to the minus 4, is 3.52. Come back to this equation. What does it say? It says that the pH of a mixture of acetylsalicylic acid could potentially have a value of 3.52 if what is true? In order for the pH to be equal to 3.52, we already know the pKa is 3.52. What does this quantity have to be equal to? 0. You can all do that math. 3.52 equals 3.52 plus 0. Okay, if it's 0 for that second part, what does this ratio have to be equal to? The log of what number is equal to 0? 1. So that means that the concentration of A minus has to equal the concentration of HA. What are A minus and HA? Go back to our original equation. This is a weak acid. This is its conjugate base. Think back to when we first did chemical reactions last semester. If this is a weak acid, whoops, sorry about that. If this is a weak acid, what does this have to be? Not necessarily weak, but it has to be a base. And if this is a base, what does this have to be? An acid. Acids react with bases to make acid plus a base equals a salt and water. Well, there's our water. Where's our water? Acid plus base, HA plus H2O, gives me a salt. Where's my water? Doesn't an acid plus a base equal a salt and water, Thomas? I'm sorry? Water is going to be amphoteric. It can be either an acid or a base. But if we learned way back when that an acid plus a base equals a salted water, where's water as the product? It's aqueous solution. There's water floating around in this whole thing. Did we make any water, though? No, we didn't. So does an acid plus a base always equal a salt and water? No, it doesn't. An acid plus a base always gives you an acid and a base. So everything that we told you about acids plus bases equals salts and water, guess what? It's not true. Acids plus bases always give you an acid and a base. So for any weak acid like aspirin, and you react it with water, you're going to make an acid and a base. And if the concentration of ASP minus equals the concentration of HASP, then pH equals pKa. What happens to the pH if the concentration of the conjugate base is much less than the concentration of the weak acid you started with? Go back to that Henderson-Hasselbalch equation. It ends up that this is a very easy equation to memorize, which is another reason why I try to avoid it. I'll show you how you can always write it down just from scratch. If the concentration of A minus is much less than the concentration of HA, so this ratio is much less than 1. The log of a number much less than 1 is positive, negative, or 0. Let's see, the log of 1 is 0, so the log of a number less than 1 has to be negative. So this is telling you that if you've got much less A minus than HA, your pH has to be less than your pKa. What did we say the pKa was for aspirin? 3.52. What did we calculate the pH of our solution was? 3.26. Why is the pH of our solution less than the pKa? Go back to that last statement. If the concentration of A minus, the conjugate base, is less than the concentration of the weak acid, you have to get a pH that's less than pKa. You can't say a whole lot about the range. The range we'll get to later, but for right now you know the pH has to be less than the pKa whenever A minus is less than HA. What if A minus is greater than HA? What's going to happen to the pH? Is it going to be greater than, less than, or equal to pKa? It has to be greater than. If they're equal to each other, it's actually equal to the pH. All right, try this. Isn't the pKa related to the pH halfway through the reaction? You've had 113 already? Yes. Those of you who've had 113, remember the experiment where you had to titrate to the half-equivalence point? What's true when you're at the half-equivalence point? Ooh, we have to think about this one for a second. I'm going to come back to this question. Let's draw a plot here. pH, volume of base. Those of you who've already had 113, this is a chart that I'm appalled that you never have to make. Okay? If you make a plot of pH versus volume of base added, let's think about what this thing looks like. If I'm titrating HCl plus sodium hydroxide, a strong acid with a strong base. Okay, you start with 0.1 molar HCl. What's the pH of 0.1 molar HCl? Is HCl a strong acid or a weak acid? Strong. So if it's a strong acid, it completely breaks apart into its ions. So if it's 0.1 molar HCl, what's the hydrogen ion concentration? 0.1. What's the negative log of 0.1? 1. Thank you. So we start with a pH of 1. Okay? I've got 50 milliliters of it here. And I take 1/10 molar sodium hydroxide and add it to it. First of all, how much sodium hydroxide do I have to add to completely neutralize all of the HCl? If I start with 50 milliliters of 0.1 molar HCl, how much 0.1 molar sodium hydroxide do I have to add to completely neutralize it? 50 milliliters. So if I start with 50 milliliters, I'm going to do a little math in my head here. I have 50 millimoles of H plus. How did I get 50 millimoles? 50 times 10 to the minus 3 liters times 1/10 of a mole, or excuse me, I have 5. Times 0.1 moles per liter equals 5 times 10 to the minus 3 moles. So 50 times 0.1 is just 5 millimoles. If I add 5 millimoles of base, then I will completely neutralize all of it because it reacts 1 to 1. What's the pH when I've added exactly the same amount of base to the amount of acid I started with? 7. In the case of a strong acid plus a strong base, you're going to get a pH of 7 when you've added the same amount. So here's pH 7. Here's 50 milliliters. So we start here. At the equivalence point, we're there. At the half equivalence point, the half equivalence point is just 25 milliliters. At the half equivalence point, how much of the HCl have I neutralized? Half of it. So what do I still have left? Well, I started with 5 millimoles. I've neutralized half of it. So I still have 2.5 millimoles of H plus, right? What's my total volume at the half equivalence point? 75 milliliters. I started with 50 milliliters of acid. I added 25 milliliters of base. So I've got 2.5 millimoles in 75 milliliters. The nice thing about this is the millis cancel. So if I just do 2.5 divided by 75, I get, thank you. So that means I've got 0.0333 molar H plus still. What happened to the sodium hydroxide? What did I make? HCl plus NaOH makes water. Do I have to worry about the water? No, it's just water. All right, so what's the pH of this? Do you happen to take a negative log of that for me? equals 1.48. So you're at the half equivalence point, and I go up here to 1.48. That's about right there. That's for a strong acid plus a strong base. If I keep doing this, what I find out is that this curve looks like that. That's what happens when you titrate a strong acid with a strong base. Do the same thing now pH, volume of base, except this time, oops. And I'll tell you right now that this is much more confusing. Now we're going to take that reaction. That's the equilibrium between a weak acid and its conjugate base. When I add sodium hydroxide to this mixture, what does the sodium hydroxide react with? We've got an acid, and we've got a base, and we make an acid and a base. It's going to react with both of the acids. A base will always react with an acid, no exceptions. All right, so I dump sodium hydroxide into this thing. Is sodium hydroxide a strong acid, strong base, or a weak base? Strong base, which means it completely dissociates. Do you think a strong base is more likely to react with a strong acid or a weak acid? Strong. Strong acids and bases will react first. All right, there's my equilibrium. My Ka for this reaction is about 10 to the minus 4. It's not very strong. Okay? How much H3O plus do I have, relatively speaking? A lot or a little? Why a little? Because it's a weak acid, you only make a little bit of product. Okay, if there's only a little bit of H3O plus in there, and I dump in this much strong base, what happens to that little bit of H3O plus? It gets used up. When it gets used up, what does the sodium hydroxide react with now? The only other acid that's there. And so it uses it up. When it uses up the HA, when it reacts with the HA, what does it make? This is where you have to be careful. When acetic acid or any weak acid reacts with a strong base, an acid plus a base makes an acid and a base. What does it make? HA plus NaOH goes to form, this is an acid, this is a base. What do I get as products? An acid and a base. What are they? Water. And, well, let's see, NaA. Is this, one of these has to be an acid, one's a base. Which is the acid? Water. So this must be base. Acid plus a base always makes acid and base. All right. This is that stuff. Why? All group 1 compounds are soluble. Why do I always pick on sodium in these? Because you all remember that all group 1 compounds are soluble. So sodium A minus, whatever A minus is, remember HA is a generic formula for a weak acid. Whatever the anion is will be a base. And when you combine it with sodium, it falls apart into its ions, and so you get sodium ions, which we don't care about, and we get A minus ions, which we do care about. So when you add base to this, you're going to be increasing this concentration and decreasing this concentration. And so when you're at the equivalence point, if we start with 50 milliliters of 0.1 molar HA, first of all, do you start with an acidic or a basic pH? HA is a weak acid, so therefore you have to start with an acidic pH. Is it going to be as low a pH as a strong acid? No. Not likely. So we're going to start up here at about 2, approximately. At the equivalence point, when I've neutralized all of this weak acid, I used it all up. What did I make in the process? A minus. A minus is a base. What is the pH when I've neutralized all of that weak acid? Is it pH 7, greater than 7, or less than 7? You made a base. If you made a base, the pH has to be greater than 7. So the pH at the equivalence point now is up here somewhere. I don't know what yet. We're going to figure that out in a little bit. But at the equivalence point, when it's a strong acid and a strong base, the equivalence point has a pH of 7. Because what do you make? You make water. When you react the strong acid or strong base with a weak acid, you make a weak base. And so you get a pH that's greater than 7. What is the pH at the equivalence, at the half equivalence point? When you're halfway there, which is where we started this question, what is the pH at the half equivalence point? When you've neutralized half of the weak acid, how much of its conjugate base have you made? Exactly the same amount. If I start with 5 millimoles of weak acid and I neutralize half of it, I've used up 2.5 millimoles. How much weak base do I make? 2.5 millimoles. What's this ratio equal to at the half equivalence point? 1. What's the log of 1? 0. So if you're at the half equivalence point, you get pKa. So that whole experiment is for you to figure out the pKa. I think it's of acetylsalicylic acid, which you all now know is 3.52. I'll see you on Wednesday.